Okay. Good morning, everyone. So today we will start to lecture related to the one of the four most important reliability issues, and the first one we will talk about today, which will be the interface charge, and also in the end related to what we generally call as a bias temperature instability. So first of all, so what you can expect to learn from these lectures. So first of all, we will talk about the different type of the oxide and interface charges. That's pretty well known that in all kinds of the semiconductor, we always have these four different kind of the interface charge. The first one is a mobile ion, fixed charge, trapping charge, and interface state. So, and then also we will explain their physical origins, and also we will to further understand the interface charge and then the trapping related issue. For sure, we have to understand that how possible the charge can be injection and transport in the dielectric. So we have the several very well known like the charge transport mechanism. The first one is FN tunneling, and the second one is a direct tunneling, and also we have this what we call the hard carrier injection. And also we will lecture how to analyze effects of a trapping charge, interface charge on the MOS device performance. Especially we are interested in the threshold voltage shift and the transconductance degradation, because in the end the transconductance degradation is related to the mobility. This could be related to the mobility degradation. And also we will talk about the difference between the NBTI and PBTI. So BTI can be divided by the two different kind of the type, which depends on our positive and negative bias. In the case of the positive gate bias, that's we call the PBTI. In the case with the negative gate bias, that's we call as a NBTI. So we will talk about the typical mechanism and what would be the possible physical origins. And also we will talk about the different measurement and characterization techniques that's very often used to help us to analyze interface state density. For example, the CV measurements, conductance, DLTS, and then the charge pumping. That are very well known and very often used in the practical aspect. And also we will assess the different BTI induced mechanism, degradation and recovery. Especially when we talk about the realistic device operation, we are not only consider for static, but also we consider for the dynamic behavior, because in the practical operation, device is turned on off simultaneously, not always in the on or always in the off. So we have to understand the dynamic behaviors as well. So first of all, we will still come back with the basic oxide property. In this lecture, we mainly focus on silicon-based phenomenon. So we talk about the general issues like interface charge and BTI in the case with silicon. But because of silicon is the most the well-known material, and then we have the most comprehensive study in the silicon-based device reliability. But the further understanding of the different semiconductor, especially the advanced semiconductor, we always can use the understanding of the silicon as a basic foundations. So we talk about the oxide property. We will talk about the charge and defects in the oxide, and especially the charge injection in the oxides. So first of all, we have to understand that the requirement for what's the requirement for the good dielectrics. So first of all, it has to be reproduce, growth, and also very important is uniform thickness. So that's a very important part for the what we can call as a good dielectric. And also we want to this dielectric has a no or minimum charges and defects. That's what we actually look forward to have. So of course, it's impossible to have the no charge or no defect, but we want to have a minimize of this effect, and that can be also acts as a good diffusion barrier. And also ideally, we hope our gate dielectric has no leakage currents under the operations. So that's an ideal case. And we want to have the large breakdown voltage and also very long time to break down. So that's what we actually expect for our ideal gate dielectric. So we are not only have the good breakdown voltage, but also the very longer time to break down, because longer time to break down is also reflect to us longer lifetime. So that's what we expectation for the good dielectric. And then the most well-known dielectric we are using in our semiconductor for sure is silicon dioxide. So that's why we also will talk about why the silicon dioxide is a very suitable, it's a very good candidate for our dielectric. There's several important aspects for the silicon dioxide. So first one is this is non-crystalline insulator and very high energy band gap. So in the case with SiO2, we have the band gap around 9 electron volts. So that's a pretty high, very large band gap. And also it's very important for the one of the critical features for the silicon dioxide is very easy to grow on silicon with a very low defect density. And also it's very easy to integrate in the process, because when you try to make a device, you have to also think about how to integration of one kind of process in the aspect with the whole process flow. So the silicon dioxide is very easy to integrate in the whole process. And also very important is that this interface state, that's generally what we denoted as a DIT. So interface state can be electrically neutralized, for example, by using the hydrogen annealing. So that's very well known in the case with the silicon dioxide on silicon. And also it's very stable and insensitive to the following process state. And also in the past, we consider the SiO2 might have the good scaling possibility, but now this is not true, because of once we start to scaling down to the SiO2, we start to face a certain issue we will talk about later. And also this is also not true, that there's no real candidate for replacement. Right now, maybe it is true, because if we consider as an interfacial layer, we might have very thin SiO2, but in the whole state, gate state, we actually will consider some other dielectrics here. So when we talk about the scaling possibility and no real candidate, we also have to mention that in the nowadays technology here, we are not only consider the case of a pure SiO2. So if you look at nowadays for the most of the semiconductor technology right now, for sure that we still hope to have the silicon dioxide, but silicon dioxide is not perfect. So normally this is because of the issue is related to that if you try to plot the band gap versus the dielectric constant, and we normally see this kind of the trade-off where the dielectric has a larger band gap. For example, like a case with SiO2, we have a 9 electron volt, but always suffering the low dielectric constant, which is 3.9 for SiO2 in this case. But on the other hand, the one with a lower band gap, for example, the hafnium oxide, which has a 6 electron volt, although it has a lower band gap, but always has a large dielectric constant, which larger than 20 here. So that's why this gives us a great possibility to think about where the chance to combine the both of the silicon dioxide with the other material, and the material we consider as a dielectric constant larger than silicon. This is a material that's what we call as a high K dielectric. So if you are a little bit familiar with the nowadays technology, what we really have right now is not the pure SiO2. It's always in the first layer we have the silicon dioxide as an interfacial layer, and in this case we have the low, although we have a lower dielectric constant, but we have the very large band gap, and then we deposit as a 1 nanometer in the most of the case. But also we will try to have another dielectric for example, the hafnium dioxide here, and then the hafnium dioxide has a larger dielectric constant, which that's why we call as a high K material. So in this case, this is a typical gate stack that we call as a bilayer. And the reason why we want to have this bilayer structure is that because of the issue for the silicon dioxide is that the dielectric constant is very small. So if you come back to the typical current equation, which our drain current is proportional to our oxide capacitance, which is equal to dielectric constant over our oxide thickness. So the only possibility to increase the current can be the two possible way. One is try to make our oxide, our dielectric, as thinner as possible. That's we call the scaling. But if we continue scale our SiO2, we will face the issue with very high lead current, where we will talk about in the next chapter when we talk about TDDB. Then you will understand that it is not possible to continue scaling of our SiO2 because the lead current will become very high, and then we will have a phenomenon that we call as a direct tunneling. So therefore, another possibility is that we try to find a material which has a larger dielectric constant. So if we have the material has a larger dielectric constant, that means that it is also possible to boost our output current. So that's why two possible ways to increase the current. One is reduce our oxide thickness. Another one is increase our dielectric constant. So that's why in the end, we hope to find out the material that can have the high dielectric constant. So that's why we come up with this kind of a bilayer, because in this case, we can always have this high dielectric constant as a material to boost our current. So that's why this is there's one particular name for this technology that we call as a high K. But at the meantime, we also not only use a high K, but also the metal gate. So if you try to look back the history of the semiconductor development, there's one dramatically improving the performance at the one technological node that we call as a high K metal gate, because at the moment we start to leverage the high dielectric constant material to boost the current. And so in the case with but still the SiO2 still will be the most important dielectric, because it has a very several good properties here. So if we want to have the certain dielectric, for example, the SiO2 has a very good reliability. Must have the several following features. The first one, it must be has a very low gate current. Because as you know, once we apply the positive gate bias on top, we always have this gate current issue, which is due to the quantum tunneling issue. And then second one, the low defects. So it means that we hope our dielectric inside the material has a low density of the defects. And also the last one, the interface between the dielectric and semiconductor is always not that perfect. And because of there's no perfect, we always has issues, what we call the interface states. So we also hope we have the lower interface states. So that's the requirement for dielectric and what we expect that if we want to have a good reliability, what is actually the expected properties. So here is some more numbers for our thermal-grown SiO2. As you know, when we try to have silicon dioxide, we can have a different process. And one of the well-known processes by using the thermal oxidation. And of course, we have the certain CVD deposition, ALD based SiO2. But the best one is always the thermal-grown silicon dioxide. And with this, all the properties, the most important one is this dielectric constant 3.9. This is number that you should keep in mind, because of this is a number that how we define as a high K or low K material. So any material that has a dielectric constant larger than SiO2, that's what we call the high K. And then any material that has a low dielectric constant lower than 3.9, that's what we call the low K. And also another important property is this, the energy, the band gap here, which is around 8 to 9 electron volt. So in here we will try to describe some more about the ideal oxide and then the real oxides here. So as we already mentioned, the ideal oxide should be defect free. So we don't have the charges in the oxide, nor allow energy state in the forbidden band gap of oxide or silicon. And also the perfect insulator. So therefore, if that's a perfect insulator, ideally there's no carrier transport through the oxide. But of course, this is not possible. We always have this transport in the dielectric in the oxide here. So the left hand side is one of the band diagram that normally, if we try to understand the MOS system, this is a metal, this is oxide, this is a silicon. So we can have this typical band diagram to illustrate the MOS the system here. And we always have the defect and allow energy state are always existed at the interface. Defect and allow energy state are always existed at the interface and then the bulk of the oxide. So first of all, if we try to look at the band diagram, where are these defects and then the allow energy state? So here is a place where we have this interface state, because this is the interface between our dielectric between our silicon, and ideally this is a forbidden band region where we won't have any state, we won't have any energy state, but because of the discontinuities between this interface and also the SiO2, so we always have the allowed energy state here. If you don't fully follow up the idea of the energy state, then you should go back to look at the semiconductor physics and device. In the semiconductor physics device, in the one chapter when we talk about the Schottky and semiconductor, when we put the metal and the semiconductor, we already talk about that in the between there's a state, because you try to stop your silicon growing in the sun region, and therefore there's a certain discontinuity layer, and therefore this discontinuity layer will in the end create the allowed energy state. So if you don't really understand what does mean the allowed energy state, you have to go back to the look at the semiconductor physics and then the device, especially in the case with the Schottky metal versus the silicon. We already have mentioned there's an interface state layer. So that's a region where we have this interface state. And also, on the other hand, where is the defect? So the defects can be possibly existing everywhere in the dielectric. As long as our dielectric is not perfect, we always have this the defects. But then how this first we need to have the allowed energy state. We need to have this defect that's waiting for the electrons being injected, but therefore we must have this injection as a action. So once we apply the positive gate bias here, as you know, once we apply the positive gate bias, and as long as the gate bias is larger enough, we have the inverted electrons, right? So we have the inversion electrons between the SiO2 and silicon. That's how we start to have the current transport. But this inverting electron will be attracted through toward the left, because right now we have the positive gate bias here. So therefore, it's very straightforward. Can be expected that this electron will be attracted toward the dielectric, because we have the positive in the left hand side. So for sure your negative electron will start being attracted and injected to the left hand side. And that's why we need to understand the charge injection and also the conduction mechanism, because how these carriers being injected from the right to the left, that's also one of the main reason leading to these trapping issues. So as long as we have this inverting electron being injected from left to the right, and whenever they see this allowed energy state, they will start to be trapping here. So then you will see certain amount of the electron being fixed at this region. That's we call the trapping. Also, certain amount of electron will be fixed at this defect inside the dielectric. That's how we call as a trapping. So the electron, the trapping means that now the electrons are captured by the interface state or defect. So this phenomenon, that's how we call as a trapping effect. But also had to be aware that the electron can be captured by this allowed energy state by this defect. But once upon a time, there's a chance that the electron can skip away from this defect, and that's what we call the detrapping. So that means electron fixed captured here has a chance to leak away as well. That's what we call as a detrapping phenomena. And also, this charge injection from left to right in the end will cause the leakage current issues. So the charge injections and conduction mechanism are responsible for the leakage current. So that's why in the later slide we will start to talk about what kind of defect allow energy state, and what kind of the charge injection and conduction mechanism responsible for this leakage current. So when we talk about the charges or defect in the outside, generally we can divide by these 4 different categories, which the first one is a mobile charge, second one is a fixed charge, third one is an interfacial trap charge, and then the last one is a bulk outside trap charge. So how do we understand this? It's better to use this schematic to illustrate. And one thing I want to emphasize that this schematic was coming out from this very old literature from 1967. This researcher already made a very comprehensive reporting that all 4 possible different charges that can possibly inside our dielectrics. But nowadays, with almost 60 years, more than 60 years passed by, that we still think that what he's summarized at the moment nowadays is still quite true. We're still facing the issues, even so many years have been passed by, we still face the same issue. Of course, the reason why we face the same issue is because we use a new dielectric, we use a new semiconductor material, we have a different vertical, we have a different plan, we have a different process, and in the end, all different kind of charge will still come out again. So the first one in here we would like to introduce is this one, where we have already mentioned. This is what we call the interfacial trapping charge, as shown here. And in most of the time, we can characterize this as what we call as a DIT here, interface trap density, or sometimes we call the interface state density. That's a DIT. So the DIT is one of the important figure merit to evaluate the quality of our dielectric interface. And then we go further inside the dielectric, and the next one we normally see is what we call the fixed outside charge. this fixed oxide charge, which is this one here. And this fixed oxide charge can be due to the certain process issues or certain interface and dielectric original properties. So as long as you deposit, you always see that there's a certain amount of charge being already stay in the interface, but not like interface charge as a little bit upper than the interface charge. And if we go further, then we will see the another one, which is happening inside the dielectric. That's we call the oxide trapping charge. Why we call the oxide trapping charge? Because this is the charge that's happening inside the dielectric. It's not a near interface. It's already a little bit has a further into our dielectric. That's what we call the oxide trapping charge. And also the last one that's very often seen in our real device is what we call the mobile ion charge. So these are the generally the 4 different categories that what can be the all kind of the charges happening in our dielectric and also the semiconductor interface. So in general, these 4 different kind of the charge will have the influence of threshold voltage, as shown here. This is the typical equation related to the threshold voltage. Threshold voltage is not only related to the metal semiconductor work function or the surface potential. Sometimes this threshold voltage will be highly influenced by fixed charge, by mobile ions, by trapping charges. So that's why it's difficult to fabricate the threshold voltage, the device that has your expected threshold voltage. If you expect your device has a certain threshold voltage around 1.5 volt, but in the end you always found out that the real threshold voltage for your device probably is less than 0 volt. And this is because of that all these threshold voltage will be influenced by these additional charging effects. So if we look at for this mobile ionic charge, so that can be the impurity, ionic impurity in the oxide, such as this different ionic impurity, and this can be due to several possible origin here: vacuum pump oils, the chemical mechanical polish, or certain contamination. That all can be possible. It's difficult to conclude what can be the pure reason, that as long as we have additional process, additional gas, additional process, that will always introduce additional mobile ions here. So the ionic impurity can be moved with polarity of the electric field. The polarity of electric field means that this is highly depends on our bias, and also that's related to our temperature. And in the end, that will always cause the IV hysteresis. So what does mean the IV hysteresis? The IV hysteresis here can be when we talk about the interface charge or BTI, we actually prefer to look at this IDVG characteristic. But what we are actually interested in is we are interested in this double sweep. We sweep our ID from low voltage to the high voltage, and then sweeping back from the low voltage. So we sweep from low to high. Then we sweep back from the high to low. And therefore we can see there's a shift of our threshold voltage here between the low to high and high to low. And then the difference between these threshold voltage we can define as a delta VTH. Thus we call this as a hysteresis. So normally, how do we evaluate the impact of the mobile ionic charge? We can always do this IV double sweeping measurements. And also, we can do, for example, this bias temperature stress. When we do the stress at a different temperature, then we will see the flat band voltage shift. And this is a measurement done on the CV measurement. And then once we have this flat band voltage shift, then we can start to estimate this mobile ion can be expressed by the oxide capacitance times our delta VFB here. So here is several possible solutions that just for your reference, but to be honest, this probably can be only effective in the case with the silicon and also with the SiO2 and also with the very old technology, because nowadays the different process, the different dielectric that will cause a different possible way to minimize this mobile ion charge. And the next one is oxide fixed charge. So in the case with silicon, we often see these positive charges. That's probably due to the structural defect near the silicon dioxide interface that we consider as a transition region. This is because related to the oxidation process depends on oxidation ambient and temperature, cooling condition, and even the silicon orientations. So, of course, there's a very difficult to justify the one pure origin, because this fixed charge will highly depend on your substrate and then the condition that is when you do this for the oxidation. But one of the typical case here can be seen in this figure. This is a figure of the oxide charge versus annealing temperature. So in this experiment, they show that by using the dry oxidation and the increase the temperature, dry oxidation to increase the temperature, then we can reduce the fixed charge here. But of course, this is coming from the very old experiment that's only conducted in the SiO2 on silicon. But nowadays, you have to try out by the different process with collecting your own data to think about what would be the possible way to reduce the oxide fixed charge. So we can also use the flat band voltage. We can use this flat band voltage shift to try to characterize our oxide charge. So if we try to characterize in the MOS cap, then we, for sure, in the most case, we can only use the CV characteristic, and then the parameter we are interested in is this delta VFB, the flatband voltage shift, and this is exactly corresponding to the transistor IDVG curve, where we are interested in as a delta VTH. So basically, you try to characterize the delta VFB that's almost equal to the same phenomenon of the delta VTH here. So here is one example that we can try to consider the measure flatband voltage minus the ideal flatband voltage. Then we can get this delta VFB, which is equal to minus QF over C arcs here. So that's a pretty simple calculation. We just try to use this flatband voltage shift to estimate our oxide fixed charge here. And the bottoming are the two cases that where we might have the positive and negative in reality. Everything can be happen. Sometimes we have a positive, sometimes we have a negative. There's no restriction that on either positive or negative only. In reality, both can be happen. So if you look at the bottom CV curve here, this is ideal. But now if we have this positive oxide charge, that will cause our CV curve shift to the left. Also, if we have this ideal CV shown me here, but now if we have this negative oxide charge, that will cause our CV curve shift to the right. So the positive and negative oxide charge in the end will influence our flatband voltage, but also in the end will influence our threshold voltage as well. So the positive or negative charge in the box due to the trapping electron or holes here. So electrons are trapped and distributed through the oxide layer. Now we are talking about the oxide trapping charge, which is here, this region. The oxide trapping charges. So in the case with the oxide trapping charge, we can have the positive or negative charge that's due to the trapping electrons or holes. So electron traps are distributed through the oxide layer. And then the hole traps are located near the silicon dioxide interface. And as I have to also remind that this is a very unique case in the case of the silicon dioxide on silicon. So in the case with silicon dioxide on silicon, we understand that the electron trapping might inside the oxide layer, and then the hole trapping might only near the Si and silicon dioxide interface. But however, this is not a universal truth. That has to depend on all your process or your semiconductor substrate. But in anyhow, the conclusion is always, if we have electron trapping, we always cause our IV curve or CV curve as a positive shift. And then if we have the hole trapping, we always cause our curve negative shift. This is very important because this gives us a certain sense, certain way to identify where we start to have electron trapping and hole trapping. As long as you see your curve shift to the right, then you can immediately in the beginning guess that might start to have electron trapping. Then the next stage we need to figure out why there's electron trapping, how does the electron injection, how the trapping happen. But anyhow, by consider this positive or negative shift, that already has a very good first level for understanding what can be the possible reason for these trapping effects here. So in here, just list several possible origins. The first one is damage generated during the process after the oxidation growth. And then also there's a possible due to ionization, radiation, charging effect during the plasma processing. But anyhow, it can be related to the process. So that can be the process related. And second, which is most important for us, this is a defect generating during the operation. And especially the second one is something we are interested in because this is an additional defect that being generated during our operation. So we might have the high electric field stress, we might have the high carrier injection, or if we talk about the space application, we might also have some radiation effect that will always give us a certain additional defects. And also, the last one is a box oxide trapping. So when we talk about the oxide trap charge, that's also there's one category that we call the box oxide traps here. And the reason that the category for here is getting more and more complicated because with the time passed by, we cannot always use one kind of defect to explain the reliability, to understand the reliability. In the early time, people only proposed the interface state, but later they found out that the interface state is not only the pure reason. There's a trapping inside the dielectric, but once they trapping inside dielectric, they found out that we have a different depth of the trapping. We have a different trapping depth. So in the region where we have the trapping a little bit far from our interface state, but not that far from the really inside the dielectric, that we call as border traps here. So if you look at this right hand schematic, this is a very well known schematic if you are working in the reliability field. If you work in the advanced semiconductor, you cannot avoid this schematic. So this schematic shows us that in the first, we have this interface state that we already mentioned here. This is a region where we call as an interface state. And then beyond this, we start have the defect in this region. This region is a little bit deeper, far away from interface state, but not that far away in the middle of a dielectric. And therefore, this region that we consider as a borderline. Here you can see, this is what we call the borderline. And therefore, the trapping here, that we call as a border trap. And then beyond the border trap, we start have this box trap, which box trap is a pretty deeper inside the dielectric here. So If we talk about the bulk oxide trap, these are the electrons trapped and hole trapping located away from silicon dioxide interface. You can see here this is pretty far away from this interface. That's why we consider as a bulk oxide traps here. And once we start to give the positive bias here, this electron might start to be injected from left to the right, and therefore this electron can be possibly trapping in the different regions. The first region is one we had to mention, interface state. So that's the first scenario. And secondly, these electrons can also be trapping in the border region, captured by these border traps here. And also, as long as our bias is larger enough, this electron can be further trapped inside this bulk region, in the end cause bulk oxide traps here. And then once this electron being trapped in the bulk oxide region, which is this one, because this is very deeper, that means when this electron trapping inside this region, that is shows with a very large time constant. Large time constant, that means that it will take a very long time to be trapping in this region, but also it will take a huge time to be detrapped, because this is very deeper region here. So deep trap shows a large time constant for exchange charge with the oxide bands, and therefore the charge is almost fixed. The charge almost fixed means that the detrapping is very slow. So in the end, because of this trapping here, and then it becomes almost a fixed charge inside the dielectric, it's a very long time to detrapping. This will influence on the long-term stability and almost what we consider as a permanently trapping carrier. And in the end, that will cause a long-term drift and eventually device failures. So how do we understand this text mentioned here? So we can simply draw the following graph to understand. So imagine we have the device that can be easily trapping, and as we already say, the one of the key figure merit to evaluate the trapping is the threshold voltage, the VTH. So in the beginning, we have a threshold voltage here, but then we start to give the positive bias here. So therefore, the positive bias will start to attracting electrons, and if the interface state will capture the electron, that will cause the negative, the positive shift of the threshold voltage. So in the end, this will become here, and this is due to the interface trapping. And because of interface state, interface trapping are pretty close to the interface, and these are the shallow trapping. So therefore, once we stop to give the bias, Vg is equal to 0 volt, then we can expect this electron trapping here will detrap, because these are close to interface and their time constant are very small. So therefore, with the time pass by, we can expect the gradual recovery of our threshold voltage. This is how we call this is a typical recovery phenomenon, and the recovery phenomenon is because of due to the detrapping. So if this is the happening for the a little bit shallow, only for the interface trapping, but on the other hand, if we consider the case still the same, the threshold voltage with respect to this is with respect to the time. In the beginning, we have the threshold voltage here, but now we bias the gate bias, and if the gate bias is larger enough, we might start to see the threshold voltage will shift to the right, and because of we now apply the larger gate bias, so then the buck trapping can happen. As usual, once we operating the device, we give the bias, but then suddenly we will stop the bias because now we don't operating our device here. So therefore, you will still put the gate bias as a 0 volt here. And because of now we have the buck trapping, that's a very deeper in the dielectric. It takes us so long, the time constant is very large. It's difficult to detrapping, and therefore, even we don't give the bias anymore, our VTH will still fix at this amount because of now the electrons are being trapped by the deep buck traps here. So therefore, we don't see any recovery effect, and that's we consider as a permanent degradation. So that's why this sentence, this text means that this will affect our long-term stability. That's called a permanently trapping charge, and then that will has a long-term drift and eventually device failure. So you can see now the threshold voltage is always fixed here and will not be possible recovery. So that's a pretty important implication if we have the electron being trapped by the box oxide trap. So to further characterize this the detrapping phenomenon, actually the trap can be also with using a certain number to be characterized. And what we normally characterize by consider as a trap energy level and also the capture cross section here. So this is a typical way to characterize the trap here. And when we consider the EP here is our trap energy level EP. So we have the this energy level to describe this trap as this here. So once you give the positive gate bias here, you have the electrons, and then the electron might start to fall into this region and then trapping here. So that's why the ET is one of the key characteristics that we call as a trap energy level. But also another one is we call the capture cross sections here. The capture cross section is the one to describe the probability So this capture cross-section is just a mathematical probability to describe the trap center can capture electrons or holes. And then typically we have this value between 10 to minus 12 to 10 to minus 14. That was we consider as attractive. And then between the 10 to minus 14 to 10 to minus 18, that's we consider the neutral trap. And the 10 to minus 18 to 10 to minus 21, we consider as a repulsive trap. So the attractive means that these are the trap that is very easily to capture the electron or holes. So once we have a carrier here, because of this attractive, that means that there's a high probability that the carriers will be captured by this trap. But on the other hand, the repulsive means that the probability is way too low. So therefore, even you have the electron here, which is difficult to being captured by this trap. That's why the name is called repulsive. And then the value is very small, between the 10 to minus 18 to 10 to minus 21. That means that ideally this trap center is unlikely to capture the electrons or holes. And also, once the electron is captured by a trapping site, it can be discharged by the photons or field emission or hard carrier impersonalization. And here the discharging means the detrapping. So for example, the first possibility is a phonon-assisted detrapping. That we call as a thermal detrapping effect. So in the beginning, we have electron being trapped here. But then, because due to this phonon-assisted, this electron can be detrapping. And also, we might also have this photon assisted, because that's due to the using the light, using the illumination to help for the detrapping effect. And also, we might have this field detrapping. This is because we apply the additional field. We apply the additional field to help to close this barrier, and that's called tunneling. And the last one is the impermeabilization. The impermeabilization is mainly because of there is additional hole generations here. The hole is recombined with electron, and then because the hole can be recombined with electron, so the trapping electron trapping is disappear. So that can be also the one of the detrapping phenomenon. So anyhow, the total of the trapping, detrapping rate equation can be considered by the following, where you have the total density of the field trap versus the time, which is contributing by 3 different phenomena, where is the thermal capture, phonon detrapping, and photon detrapping, and then the phonon detrapping. So then in here we won't talk too much of this mathematical equation. If you are interested in, you can look up by yourself. But most important is to understand the physics behind. And also some people use this one in the end to extract the capture cross-section. If you need it for your future research, you can always use this equation to try to estimate the capture cross-sections. So the interface charge, the summary here, is the defects at the interface or near the interface. And then the energy level is in the silicon band gap, can exchange charge with the silicon band, and characterized by trap density, DIT here. And also the occupancy depends on the silicon surface potential, and also we might have the different type of the interface state. We have acceptor type, we have the donor type. And slow and fast interface trap can all be possible from the time scale between the picoseconds to hours. And this will influence on the CV, transconductor, leak current, and noise level. And we can measure by this interface charge is very often measured by CV or GV, that's a conductance method. So there are several possible origins in the case with the silicon dioxide interface, which is the dangling bonds or defect generated during the operation, and then therefore there's a bond breakage. And also we might use this hydrogen content ambient for the annealing that might help to decrease this interface state density. So here is just another short summary that the interface charge, if we talk about the case with the silicon dioxide, that's because due to the dangling bond, which we might have the silicon hydrogen dangling bond. And then we can perform a low temperature hydrogen annealing. Sometimes we call it a foaming gas annealing. So here is some more detail related to the interface state that can be happen in the band diagram. So the left hand side is the one we already mentioned that this is a region where we have this interface state here. But also the interface state can be divided by the two different categories. One is the acceptor line, and then the acceptor line is the neutral when empty, but the negative charge will be formed if we have the electron occupy the state, which is this one. So in the beginning was a neutral if this is empty. But now if we start this acceptor interface state capture electron, that will start to have the negative charge. And also, on the other hand, we have this another one called the donor-like state. So donor-like state is that the neutral when full, but the positive charge once the electron leaves the state here, which is this one. So the neutral is here. But also we start to have the positive charge. Once the electron leaves the state, so we have two different kind of interface state. One is acceptor, one is a donor-like. So if we talk about the summary of the oxide charge here, can be consider the different categories. So what we have been mentioned is a mobile oxide charge, oxide trapping charge, and interfacial trapping charge. And also the most often characterized that where we will use is, for example, this bias temperature stress, that's a very often used, and CV measurement is also very often used, and also the conductance method, that's also very often used to evaluate this different kind of the amount of the charge here. But in anyhow, because later the understanding of the reliability is evolved as a technology evolution. So then once the technology become more and more complicated, we found out that it's very difficult to justify the contribution only coming from the mobile charge, only coming from the oxide charge, or only coming from the interfacial charge. But in the end, all these will contribute the threshold voltage shift. All these, the important outcome for this trapping charge is all these will contribute the threshold voltage shift. And then this threshold voltage shift is highly depends on our bias temperature. Different bias temperature that give us a different threshold voltage shift. So in the end, we just all consider the one general phenomenon that cover all these three different charges. That's we call as the bias temperature instability, or we just call as a BTI. So now in the end, we just call as a BTI as a general phenomenon that all related to the trapping effect. But however the trapping, we cannot sometimes it's very difficult to clearly specify because the technology is way too complicated. So in the end, we just try to characterize the threshold voltage and try to understand why this threshold voltage shift, and then we call this phenomenon as the bias temperature instability. So another one that we have to focus is related to the charge injection in the oxide, especially as you see that the reason that why we start to have this trapping effect is, first we need to have available defect, available energy state, and the second condition is that we need to make sure this charge can be injected into the oxide. So that's we have to talk about the different mechanism that cause this charge injection here. So we will talk about the FN tunneling, direct tunneling, the hard carrier injection. So the first one is FN tunneling. So idea for FN tunneling is very simple. As long as we apply the positive gate bias here and in this region, then we'll start to pull down our band diagram. So therefore, you will start to see the barrier here is become thinner. Original is this barrier as a triangle, as a square. But now we pull down here, then this barrier is become as a triangular. So the tunneling is always proportional to the barrier height and then the barrier width. But now we see the barrier width is reduced. And because of barrier width is reduced, so the electron can start to have the higher chance to tunneling from the left to the right. That's what we call as the FN tunneling effect. So the FN tunneling is a quantum mechanical tunneling through the triangular barriers between the silicon and the oxide conduction band. And once the electron in the oxide conduction band, they travel with relatively high mobility to the anode. This is a region that we consider as an anode. And the substrate current start to flow above the 6 megavolt per cm. And then the most important is this tunneling effect is independent of the temperature, but only depends on our barrier height. You can see from the equation here. This tunneling effect is pretty related to the barrier height, which is pretty makes sense, right? Because of this barrier height in the end will determine the probability of this tunneling, FN tunneling as well. And this is a typical characteristic for the oxide, which has a 9.7 nanometer. And then in this case, this shows the FN tunneling. And here is some more detail for how we can further justify in the FN tunneling. In most of the case, people prefer to, because the equation is way too complicated, cannot to identify the result is FN tunneling or not in the first sense. So normally what we are doing is try to plot in J over E squared versus 1 over E. And if this gives us a straight line, if this is a straight line, then we can conclude that this is probably due to the FN tunneling effect here. And also, another issue is about the barrier lowering effect. So the barrier lowering is because due to there's image force, and then if there's a barrier lowering effect, then tunneling probability can increase as well. And the next one is direct tunneling. So direct tunneling is another very serious issue that's mainly happening in the very thin dielectric. In the case with the thin dielectric, we can see this is in the case with a very thin dielectric here. So therefore, even right now, we don't have this triangular barrier. This is only the trapezoidal barrier. Then the electron can already tunnel through the left to the right. So the direct tunneling is mainly due to the quantum mechanics tunneling through the trapezoidal barriers here. That's because we have very thin dielectric. So then the difference between the FN and the direct can be considered mainly due to the dielectric thickness. So the FN tunneling, which is mainly due to the thick dielectric. And then the direct tunneling, which is due to the thin dielectric. So now you can see in the right hand side, this is one of the very famous experimental results. Once we scale down our dielectric down to the 2.5 nanometer, but we only apply the 1 volt, we already have the current up to 10 to minus 4, which is 0.1 milliamp. That's extremely high. That's why people start to feel like if we continue to only scaling the dielectric thickness below 3 nanometer, is this not going to be work, because we has a very high gate current here. So this is another very famous paper, although it looks figure quality is not that good, because this paper is published by the 1997, and this paper was published by the Professor Yuan Tao. If you know, if you probably have seen his book, he has a very famous book talking about the scaling MOSFET related to all the scaling. So when he was a time, I believe as I remember in 1997, he was still in the IBM, so he already published the paper to talk about the issue of the dielectric scaling, shown here. So this is 36 angstrom, which is roughly like a 3.6 nanometer. But if you try to down scaling the outside thickness down to the 10 angstrom here, then we see the dramatically increase of our leach current, which is increased more than 10 orders. So the direct tunneling increased by 10 order of magnitude when the thickness decreased from 3.5 to 1.5 nanometers here. That's exactly show us oxide pure SiO2 scaling can cause a huge issue for the device reliability, because of right now we got a very high gate current, so we cannot continue to scale our dielectric anymore. So that's why people start to think about that we need to have a high K dielectric, because of a high K dielectric can avoid the thickness scaling. The reason why we want to do the thickness scaling, which is driven by the needed of the boosting the current, as already said, the drain current is proportional to the outside thickness, which is equal to dielectric constant over the thickness. So the reason why we want to continue to scale down of dielectric, because we want to have the higher output current here. But if we can use a high K dielectric, then we don't have to continue to always scale down the dielectric, because we can use a high K material to boost the current as well. So here is another, just one more experimental result to show that the direct tunneling is a major limitation of a scaling outside thickness here. So that's why we need to have the high K dielectric here. So this is a very thick dielectric. We have the FN tunneling, but now we scale down, we start to see the increase of a gate current here. That's because due to the direct tunneling effect. And also we have another issue that we call the bulk limited conduction here. That's because of we have if our dielectric has a large but the shallow trap density, so if we have very huge amount of the defects here, and then this defect in the end can form as a very shallow trap in this region, and therefore our electrons can be conducted from left to the right by go through this shallow trap. And this is a case where our ET is small. So if a dielectric has a large shallow trap density, the current conduction is not limited by the injection current, but by the mobility in the conduction band of the dielectric, and then charge can be hopped by the field ascending Schottky emission from one trap to the other. And this is phenomenon that we call as a Poole-Frankel emission. And this Poole-Frankel emission is strongly temperature dependent. That's also very often seen if you fabricate a device that has a very poor dielectric, that has many defects, and you will easily see that you have a highly current. That can be due to this Poole-Frankel effect. So here, just a quick summary that there are several different possible mechanisms here. The first one is the direct. The first one is the FN tunneling, and then the second one, the FN tunneling due to this triangular barrier. We have the direct tunneling due to this trapezoidal barrier, and also there's a typical Schottky emission, but also have this Poole-Frankel. And also there is one what we call the hopping conduction. It's almost like an ohmic conduction here. Okay, so we will take a break for 5 minutes. We'll come back at 11:10.
接个5分钟请教一下。其实这个章节我蛮感兴趣的，就是前面有讲到一个概念，跟我查的也是类似，就是说，我的这个 trap 是在 这个靠近我的界面，还有 border 跟 bar。那因为像我自己的有一些状况是发生说，我画一个 high K，然后有个 high K 它可能是磁值特别少，然后它的 bias stress 或者 BTI 之类的比较大，所以我们就可以说它是因为它的这种 arc trap 可能比较多，然后它的 shallow trap 或者是比较 border trap 是比较少，可以这样子做诠释。
你再讲一次，
就是说，假设我的磁质少，就是我量 CP 我的磁质少，但是我量我的 bias stress 它的那个 shift 的 wavelength 是大的，然后跟另外一个是反过来，我是不是可以说，因为是来自于它的这个 trap 在这边多还是在这边多的问题？
那 depend 你的 bias。对，如果说你在低压的时候，可以用低压跟高压来去判断到底是 trapping 比较靠近 shallow 还是看近比较低。
所以假设我用5MV 去做，
对，就是你用比较偏低压的，或者
我可能改 EMV。
对，这样你可以稍微可以，
它可能会有反曲一点。
对，它可能会有一点就是影响，就是你这个其实很直觉嘛，越低压当然它就越 trapping 在 shallow 地方，越高压就越 trapping 在 deep 的地方。
但如果今天反过来说，假设我的这个材料它是可能 trap 在比较中间，我认为，那假设我给一个5，它有8，然后我给个2，
对。
它可能反而就很低了，对不对？因为它不大。
没错，对。
反而是我可能认为差它反而会高一些。
对。
还有一个问题是刚刚有讲到一个是说，在 interface trap 有 donor lines 跟这个 acceptor line。那像这个东西，我要怎么样从我的电芯上两侧去发现？
你就看它这个，就是说这个 acceptor line 的话，它是加了电压之后它是 negative。所以它加了电压之后，你有负电引射进去，它会看你的 VTH 往入去，它就是走的三种来。
那它跟我刚刚讲的那个 border trap 有什么差？
都会同时发生。border trap 跟这个是不一样。
对，是说它在显示上可能是一样贡献。对。可能是这两个综合考虑。
你在 border 里面有 acceptor 过动。
对，我是说，我这边感觉比较像是
interface。对。
所以它可能对时间的那个 constant 更重，它波等就再长一点点。
对。
好，然后还有一个小小的问题是关于分组的问题，大家老师可能会讲，因为我是11月4号，我是这个同学。
对。
那我其实刚刚有即兴表示，因为我要去日本参加 STDM。
对。
那我这样子我没有办法，那我是不是可以换个组？我怕对其他人不公平。
那你要换哪一组？
我觉得可能就是往后拉，可能拉到24号之类的，不知道有没有办法做一个调度。或者是我可能去做报告，然后就没有办法，
可是你做报告没有报告的话，你没有上报告，你这个不会。对。
那可能不需要，因为我是真的。
那这样子的话，你可能直接你是哪一个？
这个，我刚刚有寄信给老师。
OK， 你说这个廖建宇是不是 ？OK， 好，我再想想看啊。
好，那我可能去这天。
你再觉得
？OK，还是往后讲。
好。好，在哪边？
这样子，这个已经最终就是学这样子。
对。
所以会到学到17周。
对，17。
会到17周，就是会考试需要到17周。
对。有什么问题吗？
会反映安排一点事情。
有什么？如果这样的话，就只能在16周，就是你那周要早晚上才考试。
你说如果11周有事情的话，可以。
没有，这就是全班要统一，大家要统一到16周考试。实际上还好，为什么那么快就有事情？
今天是3点看这个是不是？
对。
我大概我记得我那个下午课是上到3点10，所以我
OK， 好。 可以参考那个 Shaki Dial 有讲那个 image force story， 在那个 Shaki 里面头，Semiconductor 里面头的那个背景，对，或者 image force story。
所以它差了在这里就这样。
对对，它的 barrier。Okay, so the time passed by, so we have already after the middle of the semester, so we will talk about the group presentations here. So first of all, as already mentioned in the beginning of the class, that we have the 4 different topics, and then now we are in the first topic, and then next time we will talk about TDB, and then also the mass transport induced values, and also the electrostatic discharge. And therefore, for the oral presentation, the first thing is required to do as a very short English presentation, and each topic right now is only for 20 minutes. So because of the amount of the student in this classroom is quite a lot, so actually for each group we have the 5 people. We have 5 students. So then the 5 students and present for 20 minutes. I think that's not that difficult. Just everyone just need to have the 4 minutes. But for sure that we need to avoid that always during the preparation there's very not equal to distribute the work. Somebody might feel very lazy, they don't do anything, but somebody might very good, they take care of everything. So what we are doing for the presentation is that the student from one group is randomly selected. So I don't know who will be the one who do the first presentation is not decided by you, it's just decided by me. So I'm not sure who will be the first one. And also the time is not equally distributed. So might be the first guy, he only present for 2 minutes, but the second guy, he will present for 5 minutes. And third guy might be present only for 3 minutes. So anyhow, everyone has to be work with other people, because I don't know that who will be selected. I definitely will not be for the student presentation, you will list your name in the order, definitely not in the order you give to me, just randomly distribute, and then all the timing is randomly selected. So the purpose is that try to make sure that everyone who the group, they are very workly to very nicely to contribute, and they work with each other, because everyone in the group has to understand the whole presentation, because you don't know which time you will be picked up. So you have to fully understand the whole things together, and then that's the purpose for this presentation. So far I will give a general review for each topic. For each topic, probably like 2 to 3 hours for each topic. And I already upload the reference material in the E3. You can try to read out, and also upload the slide from the last 2 years slides. You can look at how the other students who make this presentation. So basically, you just need to use my slide as a basic foundation, and you can revise it, because each topic I talk 2 to 3 hours for sure. I'm not asking everyone to present in the 2 hours, just 20 minutes. So you can pick up any part that you feel interested in, you are understanding, and you feel something, my slide is not perfect, you can find a way to improve it. You can pick out the one that you want to improve it. So you can please revise it and then make your own version. And then also you have to work with a teammate for your group presentation. As I say that if you don't prepare, you definitely won't, you will not only to present a certain part because you are randomly being choice. So what I suggest that you have to divide the work for sure, but each member has to understand his and her own part, and then the member has to make a slide for everyone, and then each member has to teach other people about their part. In this case, then they would be more efficient that the whole group student can understand the whole presentation. That's the purpose. So that's why you have to you can divide the work and make your own slide, but in the end you need to teach other one. You need to make sure the other member can present your part as well. And in the end, the group presentation is consider only the one score for each group. So then if there's somebody in the group they don't present very well, of course they will influence the score. And here is how we do the evaluation for this one. So we have a content 40%. That will be the one score for each group. So that's everyone will share the same score for this for 40%. But of course, somebody, I believe someone in group might very good, they prepare very well, they can deliver very well, and they should get some more high score. So therefore, there will be also the score for each presenter. That will cost for the 60% as well. So that's a delivery here. And then also very important is the time control, because of I don't want the presentation too short or too long, because too long I lose my patience. Everyone lose the patience. Too short, that means that you are not work hard enough. So the score will be considered as this. So there is a certain reduction. As you, for example, if you present for 90 minutes, then your score will be 19 plus 20 absolute, 20 minus times your original score here. So that means what you have to do is you have to practice to make sure your time here is approached to 20 as possible as you can. If you do, you have present for 22, you will also get the score reduction. If you present only 15, 17 minutes, you will also get a score reduction. So I want to have very good timing control. That's a very key for the success of the presentation here. So one more thing, you need to send me the slide by one day, 9 p.m. before your presentation, and you also need to print down the 2 slides in the one sheet. That's for me, because I need to do the grading. So you need to print out the slide. Just one is enough, but that's a 2 slides in the one sheet. That's enough. Okay, so then here we talk about the schedule for the rest of the semester. So today is October 27. So here we are. Here, and I hope today probably, I'm not sure that I can make it to finish, but next week we'll move to the TDB. But also we give you certain small time that you can to discuss, to work on with your teammate. And then this is a first group presentation will be happening on the November 10th. and the second one is November 24, and also this one. This one. The third topic is December 8, and also the December 15. And then, right now the final exam is set as December 22. That's a Monday. On Monday morning, I hope that will be work with everyone. I'm not sure that I believe now in this classroom everyone are the graduate students. You know, graduate students should not have the winter vacation. So therefore, I hope December 22 is not the winter vacation yet, right? So I hope this time will work for you. But if you are not, so we only have the one exam. I don't want to have the mega exam. So somebody come one day, somebody come another day. That's cause a difficulty for me to arrange. So in anyhow, we will prefer for the December 22 on Monday. But if really cannot make it, as a majority agree, but that has to be a majority agree, then we need to set the exam on the December 15. Then that would be a very busy week because all of your exam, all of your things have been done in the December 15. And then also we need to pick up the time in the evening, or the worst case, even have to be the weekend if we need to select the time fit for everyone's schedule. So my preference will be still the December 22, but if you have any question, still free to let me know. Okay, and let's talk about the group here. That I already divide the student. Then you don't have to form the group by yourself. Now I will call your name. I will call your name, and then you raise your hand, and then the people can understand. And this also will be considered as a tendency. 陈玉姐、陈柏瑞、施承谦、马赫斯、张佑云、王伟博、陈俊显、范廷伟、陈怡珍、陶氏美惠 ，and 陈崇光、高和林、黄怡珍、曾一柔。And this group is a little bit special because Liao Jianyu, he will not be available. Liao Jianyu will not be available, so he will be shipped to the last group in ESD. So and then in this case, this group only need to present because you only have 4 guys, so you only have to present for 60 minutes. Okay. Next, 张朝杰、尤博彦、吴雅静、曹成章、吴玉慧。Next one, 曾浩、林贤昌、邱元杰、王贞杰、蒲建浩。I think it's you. PJ. I think this is you, right? Yes, this is your name. So try to remember. Then you have to also recognize your team members. 叶俊廷。Paulina. Yes. 蒋新伦、邓有福、林于仁。Next one, 江信生、江正勤、 简伟成、洪明阳、肖许恩。Next one， 董佳琪、胡宇轩、高守廷、吴伟庆、周明远。Next one， 洪世全、刘宏奇、薛启、翁成祥、罗明成。Next one， 孙正伟、陈印祥、林哲熙、林定谦、李浩哲。Also, this will plus one as a 廖，也是叫廖建宇。Because this one has 5 people, so then it will be 25. Oh, 24, sorry. 黄胜廷、刘真坤、温科月、张成佳、黄诗允。Okay, so later after this class, you will have time to meet up your students, so you can start to prepare. So all the materials and the reference has been uploaded in the E3. Okay, so back to the tunneling mechanism in this MIS interface. So this is one of the example. Actually, this slide is made by the previous student presentation. So as I say that my slide is not perfect. There are many pictures are from the very old literature. The figure quality is not that good. So you are welcome to revise it and make your own version. So this is a very nice version. So in the end, just want to illustrate the several different mechanisms. We have the Schottky emission, Paul Frankel, hopping conduction, and we have the direct tunneling, which is happening in the very thin dielectric. And oh no, that's a FN tunneling. That's in the case with around 10 nanometer, and we have very thin. That's due to the direct tunneling. So this is just example that you are welcome to revise it what I'm saying, but just use your own word, use your own figure to illustrate again. So another issue is very well known is what we call the hard carrier injection. So the hard carrier means that the carrier has gained large energy in the high electric field. So that's what we call as a hard carrier injection. So once the carrier receive enough of energy, so the carrier here can start to cross the barrier and inject it toward the one direction here. So the hard carrier can be generated by considering the large fields in the channel. That's what we call as a channel hard carrier, or large fields in the depletion region. That we consider as a substrate hard carriers here. So both hard electron and hard holes can be injected, depends on the outside field. So we can have the hard hole injection, we can have hard electron injection. So the hard carrier injection is mainly happen in the case where the device is biased in the on state. Then our VG is larger than threshold voltage here. So because the VG is larger than threshold voltage, so now we see there's a channel formation. There are lots of electrons in the channel. And the meantime, this also happening in the condition where our drain bias is pretty high, and therefore, because of high electric field, then you can see this is a simulated electric field profile, and this is a region for the source and drain here, and then this is a peak electric field will be close to the drain region. So in the drain region, we have this very high peak E field. And therefore, this high peak E field, that would be the energy for carriers. And because of this one, so we can see the carrier, this is electron, being flowed to this side because we have very high electric field. So this high electric field will push the carrier injected to the dielectric. So therefore, we will have this hard carrier injection in this region here. And this hard carrier injection will cause the threshold voltage shift, but also will cause the drain current decrease. So that's a very serious phenomenon. Actually, the hard carrier injection, you see the paper here is published in the 1985. That was just 1 year later than I was born. But right now, the hard carrier injection is still one of the critical issues in the lots of device in the FinFET, especially FinFET. They suffer a lot of hard carrier injection because now we try to reduce the length. If we're scaling the length here, then the effective electric field is getting higher. So the hard carrier injection is become pronounced. Then compared to the previous, now it's getting more and more serious as a hard carrier injection in the advanced CMOS. So here is another illustration. In anyhow, just see that there's a large electrical field and the drain side that leading to the high energetic carrier generation. And as I say that in the nowadays, if we look at the channel length decrease, then the lateral electric field actually is increased. So therefore, the hard carrier injection phenomenon is getting more and more serious. So even though this phenomenon has been studied for almost 40 years, but nowadays it's still one of the critical reliability challenges. So when we talk about the charge trappings here, for sure that there's several way that we developed in the past to do these charge detections. So there's a very standard that we can use a CV measurement. For example, we can use a high frequency CV, low frequency CV, quasi-static CV, conductance method here. And also we can use a substrate swing SS for the characterization of this charging. And also we can use the DLTS or charge pumping. These are the very well-known measurements that has been used in the semiconductor. To be honest, it has been used in the last 40 years, but nowadays still quite useful because of these measurements. With the time passed by, people come up with a new understanding of this measurement, and then also we are able to use this measurement on the new device. So in here, when we consider the summary of the interface state density characterization, in general, we can divide by two different categories. One is by using the MOSFET. Another one is by using the MOSFET here. So in the MOSFET, we have this CV measurement or conductance or capacitance DOTS. And then in the MOSFET, we can look at the substrate swing, or we can consider the charge pumping. In here, I didn't mention the noise because the noise is it's a very complicated measurement. It takes like lots of the students who work on the noise measurement for their whole PhD. To be honest, the table showing here, each category is spent. If you want to really understand the whole detail, sometimes many students they use this as their whole PhD, just focus on one measurement techniques. So in this, just also want to remind that in the first half of the class, I put more effort to explain the fundamental in detail. But in the second phase, this one I would prefer to go through this phenomenon that in the more fast way to give you have the general understanding of the whole picture, because of this one, to be honest, is not possible to be finished. If you really want to the detail, it's definitely not possible to be in the 2 or 3 hours. It's very difficult because this is kind of like the compressive of the last 40 years of knowledge. So anyhow, it's very difficult to make it as a show, but also it can be understood that you cannot follow everything, because of some of these need a certain practical testing experience. You really need to do some testing. You really see this phenomenon, then you will start to wondering why this is happening. But at least could be the good beginning for your future research, for your future job. Because in anyhow, future, once you see these key terms, you will remember that you can come back to look at the materials again. So one of the famous measurements that we are very often use is what we call the DLTS. The full name is the Deep Level Transient Spectroscopy. In the DLTS, as you see here, this is developed by the very long time ago, from 1974, and then the purpose for these measurements try to investigate the deep charge trapping level in the semiconductor space charge structure, which may be either p-n junction or Schottky barriers. So the beginning is try to develop a way that we are able to characterize the charges inside the space region, and where we have a space region, for sure in the p-n junction or Schottky barrier, we have the space charge region, we have the depletion region, and then we have to measure the capacitance transient at a different temperature in the semiconductor space charge structure. And also, because we can measure the different temperature, then we can build up the Arrhenius plot. So finally, the Arrhenius plot is coming again. The reason why we use Arrhenius plot, we talk about Arrhenius plot in the beginning, because in the end, you will see the Arrhenius plot in the many occasion we need to have this plot in the end to calculate the activation energy. And then the idea is that the fundamental idea is very simple. We just need to have the structure that has a space charge region, which is, for example, the p-n junction. If you look at the typical p-n junction here, we have a P and N, and for sure everyone here should be aware that the p-n junction will form the depletion width, the space charge region between P and N. And then because of this depletion width, that will cause the capacitance in this depletion region as shown here. And therefore, and also this depletion width has a different kind of this depletion region has a depletion width this depletion width is highly depends on our bias, our doping in the N region, doping in the P region as well. So we actually consider to leverage this capacitance induced by this depletion region to estimate the trapping and detrapping phenomenon. And how this going? We can use this one to give a first level understanding, because if you want to go deeper, it's you need to spend like hundreds of hours. But in this slide, it's enough to give a brief understanding. So what we are doing here is the first one, we fill the traps. So we give the bias here. We give the certain bias here. Try to fill the traps here. So imagine this is a PN junction. P and N here. And if we have the defects in this region, how do we characterize the defect? The idea is very simple. First one, we want to have a certain electron trapping captured by this defect. So we fill the trap. We allow the electrons flow. We give the bias. Once we give a bias, then you have the electron will start to flow and electron will start being captured by this defect. So therefore, you will start to see the electron capture here. So that's the electron trapping. So that's the first. We have the defects here. So that's why in the first state is we fill the trap here. And then the fill the trap, the purpose for fill trap is trying to induce the trapping effect. And then the second state is we start to give no bias. And then the no bias, the purpose to no bias because of we want to see the detrapping. So we have P and N here. So now we have the defect here. And then the defects are captured electron. And because of you have an additional charge inside this space charge region, and for sure this additional charge will influence the space charge width. So therefore you will see the depletion width here. The depletion width in the end will induce the depletion capacitance, right? But now, because of you have additional charge inside this space charge region, so therefore your depletion capacitance, your depletion width will be also influenced, and then your depletion capacitance will be influenced. And therefore, if we give a no bias, this electron start to detrapping. And because of detrapping, so the charge inside this depletion region start to change. Then you will see the depletion capacitance start to change. This is because due to the detrapping. So now you can see that the second phase is with the no bias, we're just waiting to see the capacitance recovery. The capacitance recovery is because of the detrapping effect. So overall, that's simple. First one, give it a pulse, we feel the trap. And then the second one, we just give a no bias, and then we let this trapping, detrapping, and then once this detrapping, we see the capacitance is a recovery. And if you characterize this with a different temperature, this is a low temperature recovery, very slow. Medium temperature recovery, a little bit fast. High temperature recovery, very fast here. So this is with increase of the temperature. And then once we have the temperature dependent characteristic, so we can start to plot the Arrhenius plot, where we have the certain amount of time versus a 1 over temperature here. And then we can have this fitting and then fit with our activation energy here. And then this activation energy means this is a trap energy level in the PN junction. So that's the ideas of this capacitance dependent capacitance DLTs. Is basically we just look at how the capacitance recovery with respect to the temperature, and then once we see the temperature dependency, we can make as a Arrhenius plot, and once we make an Arrhenius plot, then we can calculate activation energy, which is a trap energy level. Okay, so the next one is we can also consider, if once we consider interface trapping by consider the different gate bias, that's also will tune in the band diagram and then cause, for example, in this case with a positive gate bias, then original your Fermi level is here, your EF is here, but once increase the gate bias, so you're getting more and more this band, forbidden band region below our EF region. So that's cause this additional trapping here. And also similarly, this is EF. And similarly, if you apply the negative gate bias here, and therefore you will see this allowed energy state is above our EF. That means that we are doing the detrapping. We try to empty this energy state. That's what we call the detrapping. So in general, interface trap will cause this kind of stretch out in the CV curve. As shown me here, this is a typical case with a DIT equal to 0, and this is DIT equal to non-zero. So if you have a larger DIT, then you will see your curve will become here. That's a case with a DIT increase. That's due to what we call the stretch out. So this is a case with a high frequency and low frequency. So the reason why the high frequency here is low the low frequency series high, you should look at the semiconductor textbook. They will tell you. And also the bottom one is also very obvious one. You see the black one is before, the empty dot is after. So that means after the stress, the CV curve change. That's because of due to the DIT increase as well. So in anyhow, the CV is a very useful method to look at how the interface state changes. Okay, so we probably end up here. So we will continue for the BTI interface chart for the BTI next week. And so now is your time. Like you can try to meet up your team members, and then at least you know which is your team members. If you cannot find a team member, just let me know. I will try to help you to find them. So then we will see each other next week, and also next week we have the homework.